So it is my pleasure to introduce to you Agnieszka Kałamajska from the Institute of Mathematics, University of Warsaw. She got PhD in 1995 under the guidance of Professor Bogdan Bojarski, who actually is a father of this place, initiator, and for many years, a director and coordinator of this nice place. And you can actually see the small plaque on the outside of the building. Agnieszka got title of professor in 2018, and her specialty is analysis, which is very broad, but then partial differential equations, Sobolev spaces, and variational calculus. And today, the slides are not. These slides disappeared. So I say, Zoom is yours. Yes, and then just increase the. Yes, I think it's fine. Okay, so Zoom is yours. Please start.
Thank you very much for the very nice introduction. It is my pleasure to have this lecture here, and also because the sentiment to the old time when I cooperated with Professor Bojarski, who attracted me in the theory of Sobolev spaces, and so it is my pleasure to also involve that objects here in this talk. I excuse also for the technical problems I had, so that it is a little bit later. So the title of my talk is Complex Interpolation Theory and Sobolev Spaces. This is something in between of functional analysis and analysis as itself, and very important, attractive because of the applications. I will not be able to consider all that problem and to talk about them, all the related problems, but I will try to say how much is known, how much is open, and why is it still so much attractive and still can be powerful, especially it's a very nice research topic for young people. First, let me say, what are Banach couples? So I have two Banach spaces, and if there is a Hausdorff topological space, it can be, for example, Banach space such that both of them are subsets of that A, and there is a linear and continuous embedding, then we say that the pair A0 and E1 is a Banach space. Is a Banach couple. So we have a Banach couple with A with the bar, and it is about two spaces. Then, when we have a Banach couples, that is, we have given two Banach spaces, in particular, we can construct another two Banach spaces. One of them is their cross-section. The cross-section is the space with the norm, the supremum. So it is all elements which are in both that spaces, and we take the norm as a maximum of the norm if in A0 and a norm of A in A1. So this is A0 cross-section with A1. And then I can have also A0 plus A1, which consists of all elements which are sums of elements A0 in A0, big capital, and A1, where A1 is a capital A1. And as the norm, I take the infimum of all such sums of norms, norm A0 in A0 plus norm of A1 in A1. And with respect to such the decomposition of the element A. It appears that both that spaces are indeed Banach spaces, so we have another two Banach spaces. Then, an easy observation gives that the cross-section is always a subset in each of these AI, so in both in A0 and A1 with the respective norms. So it is not only the subset as a subset, but it is a Banach subspace. And each of these A1 and these A spaces, that is A0 and A1, is a subset of the space, which is a sum of the spaces. So those are, so the embeddings are as Banach spaces. And we can say even more, if the cross-section of that spaces is 0, so I say they are both in topological space. So we can say about their cross-sections because they are somewhere in a larger set. So if we cross-sect them, if it appears that this cross-section is 0, then the decomposition which we had, let me come back, that decomposition here is unique. So it means there is only one A0 and A1 such that A is A0 plus A1. So that we can say that then it is, we call it direct sum, and it will denote it as A0 O plus A1. And the norm is then precisely norm of A0 plus norm of A1. And then if we have that good situation that the cross-section is 0, then this O product is isometric to the product A0 plus times A1. So there is easy projection. We have a sum and we project it into A0, comma A1. So it is in the product, and this is isometry, it's easy. Then we say, what is intermediate space and mapping between Banach couples? First of all, suppose that we have a Banach couple, A0, A1, and we say that any Banach space A is intermediate with respect to the Banach couple if the cross-section is contained in that A and that A is contained in the sum. And that embeddings are considered as a Banach spaces. So it means there is also inequality between norms. Then, so we know what is an intermediate space. Then we know what are Banach couples. Then let us say, what does it say that there is an operator which acts between Banach couples? We say the following. It acts between bar A and bar B, so two Banach couples, if it acts is as a bounded linear map between A0 plus A1 into B0 plus B1. So this is a Banach space, A0 plus A1. This is a Banach space, B0 plus B1. So T must be from A0 plus A1 to B0 plus B1 as a bounded linear map. And moreover, the restrictions, if I restrict T to A0, then it comes from A0 to B0 as a linear map between Banach spaces. And if I restrict it to A1, then it comes from A1 to B1 also as a linear map between Banach spaces. So there should be the continuity of that operator. And then there is a notation for such operator. It is a B, like bounded from A bar to B bar. Then, if I have a function which is holomorphic, say I have a domain U in the complex numbers, and a function which comes from U to a given Banach space X, then I can say that this is holomorphic if the usual definition of holomorphism holds, but the values are not in C, but in a Banach space. So that means if I have a differential quotient, f of z plus h, and subtract f of z, divide over h, then as h comes to 0, it comes to the number in x, which is called f prime of x, no matter in which way H converges to 0. So what I say, it is the same definition, almost the same as holomorphicity in the usual way, but the values and the norm and the convergence is not in C, but in X. Then the next object is the following. We deal with functions which are defined on the strip. So the strip, by strip, I call the all integers in complex numbers, Z, whose real value is between 0 and 1, including 0 and 1. So imaginary part can be as large as we wish, but the real part is between 0 and 1 and can include 0 and 1. So this is a strip. And then if we have such a strip and the Banach couple, we, by capital F of bar A, we denote the set of functions which come from strip to the sum A0 plus A1, and they satisfy the following three conditions. First condition is that F is continuous and bounded on S. We should remember F comes from, say, Banach space, complex numbers, so the topological space, into Banach space, A0 plus A1. So we can say, and also this is a linear space, so we can say about its continuity and its boundaries as a map from S to the Banach space, A0 plus A1. Then, F is holomorphic in the interior of S. In which sense do you mean holomorphicity? In this sense, as a function which comes from a strip, U is inside the strip, or interior of the strip, and X is A0 plus A1. So that function must be holomorphic as a function with mappings in A0 plus A1. Then, if I take H equal to 0 or H equal to 1, I consider the mapping. I take real T and consider F of H plus IT. What does it mean? If H is 0, I have F of IT. So I am on the left-hand side on that strip. If I take H equals 0 and consider the function F of 1 plus IT, it means that the argument moves in the right-hand side of the strip. So then I consider such functions, and I know that if I take H equals 0, then F of IT, so when moved on the left-hand side of the strip, it is bounded into A0. But if I take H equal to 1, then F of 1 plus IT, it means I move on the right-hand side on the strip, is continuous from R into H1. So when I restrict F to the left-hand side of S, I have continuous function to A0. When I restrict F to the right-hand side of S, right boundary of S, I have a function which is continuous into A1. We should remember this. So it appears that if I have I have a set F of A bar defined on the strip. Then this set can be equipped with the norm. So the norm of a function F defined on the strip is the supremum of all the values F on the right-hand side of the strip in A0. I take supremum over all the values on the strip in the space A0. I also can take the supremum of all values of F on the right-hand side of the strip in the space A1. Then I take the maximum of those two quantities, and then it gives me the norm. It appears, which I omit, that indeed this is a Banach space. So this is a Banach space with such a norm. Functions defined on strip. They play
Excuse me, may I
the
have a
crucial
question?
role.
Excuse me, may I have a question?
Of course,
Could you please go to the previous slide?
yes.
Okay, I'm wondering whether from this condition B and C, whether it follows condition A, since if you are holomorphic in the interior, and also you are continuous and bounded on the boundary from R to A0 and to A1, which are smaller than the sum A0.
I'm not pretty sure about it, but there is one delicate thing. Bounded as S is in the closed S closure. Holomorphicity is inside. If it
Yes.
would be up to the boundary, no problem with this.
Yes, but on the boundary you are bounded and continuous from R into H. Oh, okay, I see you can
So I think
approach some
I would
point
be
on the
careful.
boundary, but
I'm not
not
able
remaining
to quickly
vertically. Yes?
answer you, but I would be careful. There is B, and B does not include the information about boundedness on S and continuity insides. It's only about the property inside.
Yes, but C controls it. Okay, but I presume that the problem is in the
Controls only the values on the boundary at the same, so it's kind of separated information.
Okay, thank you.
Thank you for your question. So we have now the norm. So we have an object, functions defined on the strip. Then what is our final most important property? Object, complex interpolation space. I take theta, which is between 0 and 1, but most important is not 0, not 1. I will tell you why. And then by A0, A1 with this number theta, I call the set of all elements of A0 plus A1 such that I will find the function f defined on strip as before. So in that class, in that Banach class of functions defined on the strip, such that f defined on theta is in the strip. It has imaginary part 0. So it is in the strip on the subset of strip of all of the elements with imaginary parts 0. So that element A is reached by f is equal to f of theta. So I consider all A such that I will find f in the strip such that that A is equal to f of theta.
Sorry, I'm a little bit confused by this theta. This theta lies in the interval 0, 1, but this function f is defined on the strip. So what does it mean, f of theta?
Yes, so 0, 1 times 0. Think about it in this way.
Okay, okay.
A real number inside the complex numbers. Very good question. Thank you for careful following. So it means everything which can be reached by f of theta. We can think about it this way. So this is a strip. I'm not drawing, but this is a strip. And from 0 to 1, we have real numbers between 0 and 1. And here is theta. So every element which can be in form of f of theta by some f in that Banach space, which were called f of bar A. So it looks very, very abstract. Very abstract, yes. It's very hard to imagine. Then we equip it with the norm. The norm of A in that space, in that space, is the infimum over all norms f of f in f defined on strip, which are reaching A as in the form that f of theta equals A. So infimum of all the admissible f. We can say such f is admissible. A is admissible by f, maybe it's more carefully said. A is admissible by F because A is f of theta. I consider all F which give me A in this way and take the infimum of their norm. So this is, it appears that this is a Banach space. It is called complex interpolation space. And it follows that if I take theta equals 0, it is A0. If I take theta equal to 1, equal to A1. And it is intermediate space for that Banach couple A0 in 1, A1, which means that A0 cross-section with A1 is a subset of this interpolation space, and the interpolation space is a subset of A0 plus A1. So it looks very, very abstract for that setting. And I can say, in a sense, one should ask, in a sense, why so abstract objects, why they are interesting. So first of all, I ask the basic question. We have Banach couple, A bar, A0, A1, and I take theta, and I ask, what is the complex interpolation space A theta for that given Banach couple? The question, as an abstract question, is very interesting because we can work and be laborious and have effects all the time. But the careful person can ask, why do we need it? Of course, remember that analyticians, as me, are people who, in a sense, almost all the time touch the problems in which they have kind of a business. They should help them to solve some problems. It's not precisely applied mathematics. It is abstract. It can be abstract mathematics, but the motivation somehow, in most situations, is related with the questions. So why is it so interesting? Why should we ask for solving this problem? How to solve this problem? What are the Banach couples? There was a statement by Calderon from 1964 which says the following. Consider two Banach couples, A bar, A0, A1, and B bar, B0, B1, and take theta from 0 to 1, not including the endpoints. Then, consider the bounded linear operator T, which acts between Banach couples. Let me maybe repeat, what does it mean that T was linear between Banach couples? It was linear bounded between A0 plus A1, linear bounded between B0 plus B1, and linear bounded from A0 to B0 and from A1 to B1. And then we ask that then the statement says the following. Consider such an operator and restrict it to the subspace, which is intermediate space. Then T restricted to the complex interpolation space A0, A1, theta is bounded linear operator from A0, A1, theta to B0, B1, theta with the following estimate. The norm of T, the norm of T S operator from A theta, let me call it, to B theta as bounded is controlled precisely in this way, is not larger than the norm of T S operator from A0 to D0 to B0 raised to the power 1 minus theta times the norm of T from A1 to B1 raised to the power theta. So we have an estimate, a boundness condition for such operators. We not only know that it is bounded from A0 plus A1 to B0 plus B1, but we have a full information about boundedness of that operator between the respective intermediate spaces, complex interpolation spaces. Let me call them A theta and B theta. And now we know this is kind of a crucial problem in functional analysis, to know that the operator is bounded between certain function spaces, and how is it bounded between that certain function spaces. Now, still this is very abstract. It can be very interesting to the specialists in functional analysis who work in the abstract setting, but I am the person who works in the setting of Sobolev spaces. Function spaces come from which are useful in differential equations, differential geometry in this way. So let us ask the simple question: in the setting of weighted LP spaces, that was first proven before Calderon in 1927 by Marcel Riche. And then his student, Olaf Thorin, has helped him. So in the LP setting, this is known as a Riche-Thorin theorem, and does not use the meaning of complex interpolation space. It is expressed differentially, but in a sense, the tools are indeed in this statement by Riche and Thorin. Then also there was in 1939, there was Marcinkiewicz interpolation theorem, which gives the upper bound, and there it doesn't use the tool, say, interpolation spaces, but now the tools in that Marcinkiewicz theorem in the LP setting are called real interpolation methods. So they originated another way to bound the operators, which describe so-called real interpolation spaces. So this is another branch. So there is complex interpolation space and there is real interpolation space. This is slightly different. So the topic which I say about now is complex interpolation space. In a sense, you will see that it is less understood than the real interpolation space. The tools are different. Now, so that was about abstract approach, about Calderon theorem, and somehow links with the LP setting of that statement, in which did not apply the tools, the language of interpolation spaces. Now, so I explained why do we need it. I'm not showing the PDEs, say the questions. There will be no time for that. But I will try to say what is open, because in that gremium, there are enthusiasts of long-standing open problems. And in a sense, I'm also such a person. So I will try to say as much and as I can, according to my knowledge, what is open, what is reasonably new, and what is the space for you, for young people, which could work on these problems. And you will be astonished, surprised, that there are so easy stated open problems. And in a sense, the new tools which appeared, in a sense, they allow to touch that problem, I will say. Now, what are weighted? So let me pass to the understanding, to the introduction of Sobolev spaces. So the basic definition. We have a domain in Rn. So by domain, I mean open set. Then on that domain, I have a weight function omega, which means measurable, can be with respect to Lebesgue measure. In fact, can be also defined more abstract, but let it be defined with respect to measurable with respect to Lebesgue measure, and positive almost everywhere. So I write it here, measurable, positive, almost everywhere. Then, what do we mean by Sobolev spaces? Let me say there are many definitions. I will use that one. I consider all functions U which are defined on the domain, and we, at the beginning, they are of class Cm. So, and all their derivatives up to order n are in LP on U with respect to that domain omega, that weight function omega. That is integral over d alpha u raised to the power p times omega dx is finite. So all the derivatives up to order n are LP integrable with respect to the measure omega dx. And then with respect, and I sum up all that derivatives, they are LP norms. I mean, I sum up all that LP norms. And this gives me the norm on WNP, but in that set, I defined it without problem. Then I take the completion of that set with respect to that norm. So that gives me complete space of the Banach space. Without
Excuse
that
me, may I have a
completion,
question?
Yes, of course, please.
I'm wondering what would happen if in this definition of a Sobolev space, without this subscript 0, instead of functions from Cm, you would consider function in C infinity, but not vanishing at the boundary. Would you get the same?
Yeah, that's a very good question. I will, when I say about the space, I will comment your question. Just give me 1 minute.
Okay,
So
thank
first
you.
of all, I take the completion. So then in this space, WMP is complete. Then if I take C0 infinity, but our C0M functions of class Cm with vanishing support, and complete this space, I have the space which has 0 in the notation, W0MP. And then coming to your question, if I understand this well, you ask, can it be, for example, that this is the same space?
Sorry, no. I'm not asking about whether this W0 and W is the same. I know that they are not, but I'm asking if in this definition of WMP, you would define it using functions U, which belongs to C infinity, not Cm, but C infinity, but without the subscript 0. So smooth function, but not necessarily vanishing at the near boundary.
Yes, I'm sorry to interrupt when you are saying, yes, we can give C infinity here. It is no problem. There are such tools, reasonably, but I would be careful for many omegas. But if for all omegas, I would be very careful. It means if omega has certain good properties, you can have Cm, you can have C infinity in that definition. But then I'm not pretty sure if for any arbitrary omega, you can have the same definition with, they say, equivalent definition by putting not Cm, but C infinity.
Okay, I see. And follow-up question, so this properties of omega somehow relates to the smoothness of the boundary or boundedness of this omega?
Smoothness of the boundary, construction of this omega, if it is very wild, one should be careful.
So this is like, for example, that boundary is, I don't know, C2. Usually, this is something which is very often encountered in this theory, that if the boundary is at least C2, then something behaves well, but if it is not, then the behavior is much worse. So
Yes,
something
there
in
are
this
many
spirit,
questions
yes?
related to the definitions. And really many ways, people can define Sobolev space. One can find very interesting overview in the book by Mazia, when it was constructed, say, in 70s, perhaps. But started much earlier, after 30s, perhaps. And those were many questions related even in the problem, the following. We have a Sobolev space, and when can I extend it outside the domain and still get the function in the Sobolev space? And what is the characterization There are really many open questions related to the construction, to the analytic, to the definition of Sobolev space, to the properties, to the densities. And even I can tell you that W0MP often is WMP. For example, on the entire space in Rn, it is so. So sometimes C0 infinity is dense in W1P. And sometimes it is on the domain, also can be with certain measure. There is no regular theory about it, which somehow shows the characterization density versus properties. Density of what? Of C, Cm, of C infinity, of Lipschitz bounded, and so on. So it means there is a reserved area talking about densities. I will come to that point.
Okay, thank you very much.
Thank you for your question. And now, summing up what I said, basic questions. Problem 1, I have two weights. What is the complex interpolation space between that Sobolev spaces? Related, one is related with omega, with weight function omega 0, the other with omega 1. They have different term of differentiability. So here is about differentiability up to M0. Here is differentiability up to M1. They are integrable with various powers. What can be said? You will see really little is known about this. Then problem 3, not WMP, but W0MP, so completion of C0 infinity in that spaces. What are intermediate spaces? No regular theory, you will see. Then your question, one of the participants from the audience, how can we somehow nicely, easily recognize that the function is in the completion of C0 infinity? Not in general space, but precisely in that narrower space. Are there some tools, analytical tools, which can be said? Because remember how we defined that space. It was a completion of C0 infinity in that space. But if we say completion, it is a very abstract tool. It's a very abstract tool, we don't see anything. And then there is a help. I will not say about anything about this because there is no space for my talk. There is analysis of trace operator restrictions and very nice tools. This is far from being closed. Also, I would say open area. Then I will try to answer this answer. There's a question, yes?
Ambient space that we embed these Banach spaces into.
Excuse me?
What is the Banach space that we are embedding these spaces into?
I would say this is a narrower space than this one. Because
yes.
there's completion of C0 infinity.
Sorry, because these W's should be forming some kind of Banach couple, yeah?
Yes, this is a Banach couple. Yes, this is one and the other. You ask in which it is embedded, in what it is embedded. From the definition of Banach couples, say in L1, say can construct it, it's not difficult, but say in many cases just both of them are subsets in L1.
Okay.
L1 with some weight. I take the minimum of the two weights. Somehow it goes somehow like that. So maybe take me too much time to precisely write, but it is similar type of space, LP weighted type space, so that both spaces here are embedded in that larger space. So was it your question?
Probably yes, but sorry, the participant already cited.
Okay.
Yes, he says that yes. I'm holding the mic, and everybody who has a question need to come to me, and so.
Okay. So now about problem 2 in weighted LP spaces. So I take one LP, weighted LP, and another weighted LP I prescribe. And I would like to ask, what is the space LP0, LP1, theta? And then I recall what is that LP? So f raised to the power p counted, multiplied by omega, the integral should be finite, and this is the norm. Now, these functions, they have values in complex number c, so it means I take the complex numbers, it has a real and imaginary part, and the modulus is as in complex number theory, so real squared plus imaginary squared, and I take it to the power 1/2. I add it and take to the power 1/2. So what is the intermediate space between LP spaces? It is precisely known from 1958. There is a description, precise description. There is no open questions in that setting. When I take P0, P1, reasonable, so between 1 and infinity, and weight functions defined on the same domain U, and I take theta, then interpolation space, complex interpolation space, is precisely LP with respect to certain omega, where 1 over P is 1 minus theta over P0 plus theta over P1. So this is convex combination of 1 over P0 and 1 over P1 related to theta. And omega is omega 0 raised to the power P over P 1 minus theta over P0. We have this number here. And P times theta over P1, this is this number here. If I see that those two numbers, they sum up to 1. So this is precisely this omega. So with the equality of norms, so that is an isometry. This is a very precise statement from 1958. So in the LP setting, there is nothing we can ask about. There is nothing new we can ask about. So let us pass to Sobolev spaces. Sobolev spaces, I have said about one way of construction, but there are some others. First, let me a little bit switch to some other Sobolev spaces, fractional Sobolev space. So I have a Fourier transform. We know Fourier transform from the course of kind of analysis, functional analysis, wherever real elements of real analysis. So we have a Fourier transform. And we take the any real S and P between 1 and infinity, and say we define the fractional Sobolev space, the particular one, which is called Bessel potential space, still unweighted, as those F, such that if I take the Fourier transform of F, multiplied by 1 plus S squared to the power S half, and inverse the Fourier transform, then it has LP norm finite. And I take the LP norm, that quantity, as the norm. So that is defined via Fourier transform, as is here, this as here. We call such a fractional Sobolev space Bessel potential space. There are many definitions. And it is known that when S is natural number, then this is the same as usual Sobolev space on Rn. So now we have Bessel potential space, and it is known, one can find it in a book by Berg and Lofstrom. That book is from 76, but the result was known earlier probably, that in that setting of that Sobolev spaces on Rn, on the Euclidean not weighted setting, this interpolation space is the same as space of Bessel potential spaces, Bessel potential space, H S theta P theta, where S theta is convex combination of S0, S1, and 1 over P theta is convex combination of 1 over P0, 1 over P1, related, both are related to theta. So there is full description, but unweighted and defined on the whole Euclidean space. So the question is, what in the Sobolev setting is known more? Now there's a weighted fractional Sobolev space, a small modification of the previous definition. We have a Fourier transform. So up to now, it is the same definition as before, but we multiply that quantity by the weight omega raised to the power 1 over p and take the LP norm of that. So previously the weight omega was 1, no change, and now we have the omega. And there is the result by Löfström from 1982 that when omega satisfies certain additional condition, which he calls polynomial regularity, then first of all, it is known that the weighted, this space of kind of weighted Bessel potential space, the fractional Sobolev space, is the same as the usual Sobolev space. But the thing is, there is such a definition, polynomial regularity condition, which is very, very strong condition. In fact, we almost very hardly will find the weight function which does satisfy the condition. So we can have Bessel potential space. It then coincides with Sobolev space, but in many cases it's not the same. It is kind of some function space. And then Löfström has proven that as far as P0, P1 are reasonable between 0 and infinity, I take theta in between 0 and 1. I take natural numbers as 0 and as 1 and 2 weights. I consider the intermediate weight described in this way. And if I know that this is polynomial regular, then there is interpolation. The interpolation space is between weighted Sobolev spaces is the same as that space of fractional order Sobolev space related to the omega theta. So there is a description, but we know we have to know that omega theta is polynomially regular. Still very strong assumption, result from 1982.
Excuse me, may I have a question? A couple of questions, in fact. First, in this, could you go to the previous slide? So you are assuming that this omega theta is polynomially regular. You don't assume it about omega 0 and omega 1, yes?
No, we don't assume that.
Okay. The second question, could you just give a glimpse, some intuition about this condition of being polynomially regular? It's like a growth condition?
Yes, not very clean, but I will tell. It is a sum of functions. Each of them can be compared with another weight, with such a weight that if I take the derivative of that weight, then it is controlled by the weight without derivative. So it is really a complicated condition. And if I take modulus t to the power alpha, then it can be shown that it does not satisfy that condition. That would be the easy weight which comes to the mind on the
this
real.
Is something like a function on which a differentiation operator behaves nicely, something in this.
It's upper bounded by no differentiation in this way. So if you differentiate, it's upper bounded by the constant type function itself without derivative. But the weight is a sum of such ones, so it's not intuitive, not a good intuitive.
Okay, and the last one, if I could, so from this theorem, one could, I don't know how, one could presume that if this condition of being polynomially irregular is not satisfied, then we don't have this equality between W and H, yes?
Yes, we can presume. However, it's not set, it is characterization with respect to the behavior of the weight function. But there are some examples
in which it is known
Yes.
that these two constructions does not coincide, yes?
Yes. So
Okay.
first, let us remember t to the power alpha on the real line is not good. And then
No, but I'm saying, I'm speaking about not satisfying this theorem.
yes, I will come back to this. So it's very easy. It's not easy, but there are constructions of the weights which have for which this equality does not hold, and the polynomial regularity condition is not.
Okay, thank you. Thank you very much.
So you see, it's very strong condition to have this property. Now, Löfström has, so that this I have said, and then there is the long time silent with respect to that theory, no papers. And then in 2019, there was a paper by Schwickel and Oinaev, and I will tell about that paper. So there are certain assumptions. Previously it was on Rm, on the Euclidean space. Now it's a domain in Rm, and the omega satisfies at such a boundedness condition that infimum, essential infimum, is larger than 0, and essential supremum is smaller than infinity on compact sets. So it's locally bounded and separated from 0. And only such omegas are considered. Then I have two omegas, two weights, I divide them, and they should be locally Lipschitz in all the statements they have. And I can say the following, that local Lipschicity condition is also a strong condition. I take the weight 2 to the power alpha, two such weights, and usually it's not locally Lipschitz. There is a condition one can easily check. So it means it's also a strong condition. Then I take theta and special space, which is kind of auxiliary space, two-weighted Sobolev space. First, phi must be in W1P, weighted with respect to the weight omega theta. And then I take phi, but multiply it by the grid of logarithm of R omega, which was here, R omega. So I take certain manipulation of the weights. I get an additional weight function, multiply it here. Here is omega theta, and this also must be P integrable. I add two things, so there is no gradient of phi, but the gradient of phi is involved in this norm. So I have kind of two-weighted function. And what they say, they have the statement saying that if the density conditions hold for W's and also for this special function space, two-weighted Sobolev space, then there is such an embedding of the interpolation space with the weight omega theta. And they say second, if additionally this logarithm of R omega is Lipschitz, then is precise information that the interpolation space is precisely W1P with that intermediate weight. But I would say the following, this is very strong condition, really very strong. It's easy to show. T to the power alpha 0, T to the power alpha 1 as omega 0 and omega 1 is not good. And then at the end, I would say why I was interested. In a sense, I have tried a very simple approach. I considered such Sobolev space that weights are not polynomially regular, not Lipschitz. This logarithm or R omega is not Lipschitz. None of the results mentioned can be used. The space looks very simple. And then we have characterization of completion of C0 infinity. Then we have certain results toward problems 2 and 3, so intermediate spaces. Some we keep working on this problem, so now we are obtaining the full characterization in the very small setting, simple setting, and it shows that this is to show you that very simple weight, very simple approach, no results. It means many things can be achieved, many issues can be checked on that field. So this is the references, but perhaps if somebody would be interested, please contact me because my time has finished, and I thank you very much for your attention.
Thank you. Any questions?
Yes, if I could ask at least two questions. One is about notation. If you could go back to the slide with this result about this interpolation.
Which result about interpolation?
Probably the last result. Yes.
This one. Mm-hmm.
So I'm a little bit confused by the notation. So now your function is defined on what? On a real line?
R plus, positive numbers.
Okay. Okay,
Very
so
small.
one dimensional, and what is this additional C after the comma?
So they think about it that they are not real valued, they are complex values.
Okay, so the domain is real, but the values are complex, yes?
Yes, the values are complex. It's not a big difference in a sense, but
Okay, sure.
theory is complex theory.
Okay, and one more question. I always wondered if you want to define this fractional Sobolev space, you need a Fourier transform, but Fourier transform is naturally defined on the whole space. So is it possible to define?
Good question.
Is it possible to define a fractional Sobolev spaces on bounded domains?
Yeah. So first of all, you defined it on the Schwartz distributions.
Yes.
But that space, a Schwartz distribution, there are smooth functions. They have dual, which is dual space to distributions, and on that space you can also define Fourier transform by evaluation. Fourier transform of the functional is the evaluation of that functional on the Fourier transform of the element. So that's why I have written S star, which is here, but I wanted to omit this information because it's too much to say. But
yes. I don't have a problem with temperate distribution. I have a problem whether it is possible to define this temperate distribution in the context of not the whole space Rm, but in the context of general domain.
There is a problem because the Fourier transform uses the whole values. It is integral over Rn. So,
exactly. So
I cannot answer you if people do something in this direction to make the narrower domain.
Okay, but so these fractional Sobolev spaces are always restricted to be restricted is not
not always. This kind of Sobolev space, this Bessel potential space is of this kind, but there are many others. So also it's a very nice branch area. How to define fractional Sobolev spaces in different way. There are many other definitions.
But not on the whole space, Euclidean space?
Can be not on the whole space as well.
So it is possible somehow, yes?
It is possible, yes. If
thank you.
You can contact me, I will tell you.
Okay, thank you.
Any other questions or comments? Maybe from Zoom people? Are you there? Okay, so if there are no other questions or comments, oh no, this is just a comment. This is okay. Yes, that was okay. Yes, finger up. So no question from Zoom, I suppose. Okay, if not, let us thank Agnieszka again. Some feedback from Zoom people. Thank you. Yeah, very happy. Everybody's happy as you see Agnieszka on. Do you see this? I guess. Clapping from the Zoom people. Okay, so thank you very much again. And I will take off the recording.